is my mic. OK, cool. Hi, everyone. My name is Shi, and I'm a security engineer at FuzzLand. So in recent years, we have seen several cases where MEV bots front-run attacking transactions. One famous example is the Curve Finance incident in 2023. The hack was due to the Viper compiler bug. Several map bots, they front-run the hacking transaction, and some of them returned the funds to the Curve. And similarly, the security company BlockStack has also front-run a few attacking transactions, rescuing funds from hackers in 2023. And also earlier in this year, during the KyberSwap hack, $5.7 million were returned by front-run bots to the protocol. So in these instances, map bots were used as a force for the good, outpacing attackers to protect users' assets. However, in 2024, the number and frequency of these stories declined. Our team has been exploring the Ethereum MEV world since earlier this year, and we have successfully prevented a few cases using the new methodologies. So in this talk, I will share how front-running works, why it has become less efficient, and the potential future directions we are exploring. First, let's look at a normal life cycle of a transaction and how front-running works. Assume you're a user and you want to send the transaction onto the chain. And you have to sign the transaction first and send it to a builder, sometimes an RPC node or sometimes an RPC provider. So block builders collect and sort transactions and send them to build a block. And then the validator, when they receive blocks, they will choose one block to finalize it onto the chain. And usually, they pick the one who's offering the biggest reward. So in real-world scenario, there cannot be only one actor here. There cannot be only one transaction, one builder, or one validator. Builders will receive a ton of transactions, put them in the mempool, where it is a buffer for putting pending transactions. They will form a block, and then this block will give a max value. And this is MEV, maximum extractable value. Also, there are more than one builder. Validators receive different proposed blocks from different builders, and they will choose the one that offers the biggest reward. So let's look at the front-running. So in the early days, the process was severely abused because transactions are in the public mempool, and transactions in the public mempool, they are basically visible to everyone. Map bots can monitor for profitable transactions, like large trades or arbitrage opportunities, and just copy them with a higher gas price in order to be included in the first position of the block. So this leads to a gas auction war, where the original transaction sender will be outbid by bots. Say I have a super powerful algorithm to find the optimal path to for different pools, but a copycat, he will just copy my transaction and add one gas to it, and he will outbid me. So all my computation power means nothing. And yeah, that's really bad for the arbitrage bots. And this is the process. When the front-runner sees the transaction sent to the builder or a public mempool, he will just copy it and with a little bit more gas to it. So the builder will put the transaction in front of the original transaction and send it to the validator. And the validator will put this block to the chain. And because the first transaction is doing the exactly same thing to the second transaction, so the first transaction will success, and the second one will just revert. This is really bad for the ecosystem. So this environment doesn't incentivize beneficial math actions. No one wants to balance the prices between different pools. Block builders, they consume most of the profits in terms of gas. And normal users, they also suffer from sandwich attacks. To mitigate these issues, private mempool came into play. So there's this group of builders who promised not to share the pending transactions with others. That's pretty self-explanatory. So private mempool, they don't leak transactions to others, reducing the risk of front-running. This was beneficial because map bots now had to compete fairly. For obvious arbitrage opportunities, the map bots with better swap path or strategy would win. The essence of private mempool also helped hide attack transactions. And also, let's look at how the process goes. So the frontrunner now cannot see the transaction sent by the user to the private mempool. So if there are two builders, one is with a private mempool and one is not, the one with a private mempool will build a block that will have a higher reward to the validator, and the validator will choose this block to finalize it onto the chain. But does this eliminate all front running? So according to our observations, many hacking attempts happen in a two-phase style. So the attacker first deploys a contract and does some preparation, then sends the final attacking transaction, which is a trigger transaction. We call these preparation phase and the triggering phase. So in both phases, the actions that the hacker performs are usually encoded in the contracts themselves. We have seen many mapbots exploiting these attacking contracts for quite some time. Essentially, whenever a new contract is deployed onto the chain, mapbots will try to exploit them. They will try to call every function inside this contract. So how do they do it? Calling a function involves extracting the function signatures. Since most contracts are often written in Solidity, or sometimes very little of them written in Viper, they follow this standard ABI conventions where you hash the signature of the function. So if the function called happened to be the final triggering function, the mapbot can front run the transaction in the future. They will know what calling which function will make them profit. So the attack and defense game between the contract deployer and the mapbots begins here. Let's assume the deployer has to use this two-phase attack for some reason. They're not using some like attacking in the constructor. Then how can they prevent mapbots from exploiting their contract? And this is really a problem of program analysis. Imagine in Web 2, when you downloaded the software or program, how does your antivirus program detect if the program is performing some malicious actions or not? And let's look at a few examples contracts to try to fool the MV bots. This is a very common pattern we have seen. A mapbot can easily bypass this. So here you have two requirements. The transaction origin and the message sender has to be some fixed address there. Otherwise, it will revert. But really, this has a very simple solution, is that you use an address hint. Usually, these hacking contracts, they are comparing the authority to their own addresses. So you just need to pass in the contract creator. And this is another type of authentication. Maybe this looks like a little bit complicated, but it's not. So it's hashing the message sender and comparing to a hash. Although hashing is not reversible, what we can do is, on the bytecode level, we just flip the equal sign, flip it to less than or greater than. That will be equivalent to a not equal to. And this requirement is just, it can be bypassed very easily. So to conclude, triggering functions with no parameters are free to exploit by mapbots. All a mapbot needs to do is to explore all potential paths in the smart contract, and there must be one profitable path. So contract deployers have to thought of a more complex functions. So this is the complex function that a contract deployer had thought of. So it takes one parameter U256A, and this parameter is a direct parameter related to the attack. Maybe there are some other parameters there. But if the parameter passed in is related to the hacking process, it's much harder to find the correct input because random inputs may not have to trigger the vulnerability inside the contract. Maybe it's a precision loss. It has to be a very exact value. However, we found that fuzzing is perfect for these types of tasks. So before going into how fuzzing works here, let's define what is fuzzing. It contains of 5 steps. First is to generate a random input. This random is not truly random from UDEV random. It's really, it has some heuristics and smart generations. But anyway, let's just assume we have this random input, and we execute the program or the smart contract with this input, and we observe and analyze the execution, collect interesting information from the execution trace, then we decide if this input is either interesting or the input is the one we are desired to. And if so, if it's interesting, some certain conditions are met, we just exit. Otherwise, we repeat and using the heuristics information we collected to generate another input. So fuzzing is a technique where we try different inputs to see if it behaves in a certain way. In Web 2, say a binary executable, maybe this is memory corruption. And in Web 3, in the context of auditing, this might be invariant breaking. I know like many Solidity developments, they now contain this process of writing invariants. And before they launch, they will use fuzzer to try to break these invariants to indicate a bug. And in the map world of Web3, the purpose of fuzzing is really path exploring. We want to find the specific path that leads to a profitable transaction. And it's apparent that the key is to generate a good input. Generating input can involve various strategies. For example, you can just use random, and that's basically the luck you need. And also, you have some constant values. These are very special values. Maybe sometimes they do some good effects on the fuzzing. For example, some small values or some addresses of 0 or max of some types, etc. And the final thing is heuristics. This is the one makes different fuzzers effective or not. So for example, you can use a multiple of 1 to the 18th. This is 10 to the 18th, sorry. So this is a very common constant in the math world or the Ethereum world. And also, there are values collected during execution. For example, if you encountered a equal check during the execution, maybe this value is very interesting. Maybe it's a password or something. And also, we adopted some methodologies open source in our ETFuzz. Our ETFuzz was basically for pre-deployment fuzzing, but it has also a lot of methodologies adopted from the cutting-edge academia side. And next question is why fuzzing? So the first reason, and I think this is the biggest reason, is it's fast. It's very fast compared to symbolic execution, for example. And in math world, on Ethereum, each block has a 12-second time interval. So when you see a contract is being deployed, you have 12 seconds to be the fastest one to do the triggering on the next block. And it's very accurate compared to static analysis. For example, if you're trying to do a full static analysis, a really thorough one, to analyze if a hacking contract is exploitable or not, it might lead to false positive, but fuzzing does not, because it's using concrete inputs to execute. And the last one is it has very low effort to build a prototype. Fuzzing, it can be a dumb fuzzer, and sometimes a dumb fuzzer can also lead to some profitable transactions. But there are also some limitations of fuzzing. So the first one is the number of input parameters. As we see in the previous example, we only have one input, A. But if the number of input parameters increases, the search space will increase exponentially. And the second one is the effectiveness really depends on the input generation. If there are very poor inputs, like truly random inputs, it will never reach the path you desired. And the last one is that it's not thorough enough. After all, it's like generating like some pseudo or half random inputs. So some specific path, like password generation thing, cannot be reached without fuzzing only. And I'd like to point out what we are doing next, and we hope the community may take a look at this. So now we are experimenting taint analysis and concaller execution to solve the third problem we mentioned before. Sometimes the heuristics can be collected from taint analysis or concaller execution to explore more paths. And also, we know some other methods that other teams are doing, like binary rewrite. They manipulate bytecode. And and also we we're really thrilled to see how this cat and mouse game continues, where people bring more Web 2 techniques into this Web 3 world. Like maybe stack analysis can help some in the MEV world, and maybe large language model will help as well. And yeah, I'm really thrilled to see. And that's all of my talk, and I'm open to any questions.
I have a question.
Hey, thanks for the talk. I just wanted to ask, you had this slide with authentication, and you mentioned that in that case, you could change the bytecode to just bypass the check, right?
Mm-hmm.
My question is, how do you, especially in an environment where you're trying to fuzz very quickly, how do you know which assertions you can bypass or not bypass? Because you did also mention that the benefit of fuzzing is that it's reliable. You don't generate a lot of false positives, right? But if you start changing the bytecode, you get false positives potentially.
Yeah, so it doesn't matter. Like flipping one byte is really quick, and that's the benefits of fuzzing. There's no much overhead to execute like 2 or 3 times. I think it happens in nanoseconds.
Okay, but if you need to generate a lot of variations, like if you have to come up with plenty of different enumerations, yeah.
Yeah, so for example, in this case, if you fail this equal and fails its require, you simply try another, there are 2 outcomes, equal or not equal. So basically, if both path fails, this fuzzing campaign fails. But yeah, that's very low overhead.
Okay, thanks.
Yeah, I have a question also. I don't know if there is someone else. It sounds like the problem sounds like a bit similar to gaming AIs, where you need to find, for example, chess. Makes me think a bit like ideally find the right sequence of moves to reach the checkmate state. So there are some algorithms that fit really well this kind of strategies, so for example, min-max algorithm and so on. Is this something that you might be exploring in the future? So for example, applying this kind of strategies to fuzzing to reduce the size of the search tree of possibilities?
Well, because this is like analyzing a program is a hard problem, and it has no solution overall. And fuzzing is like the fastest way of doing it. So maybe machine learning, it's more, I guess, related to stat analysis, where you want to have a thorough understanding of the program. But in the math world, we need speed. That's the reason.
Okay.
Thanks for the presentation. So most of the examples that you show work because the attacker are not too sophisticated, right? Because the trigger function is within the bytecode. But what happens once the attacker gets a bit better and the trigger function is not in the bytecode directly, and maybe they delegate call to another contract later on that you don't know? Do you have a heuristic for that, or how you consider it?
Yeah, that's, I think, is the final state of a unbeatable hacker who hides all his payloads in the final transaction, and this is a one-shot transaction, and send it to private mempool, and no leak from private mempool. That's the final state of a really sophisticated hacker. But as of 2024, we have seen a lot of 2-stage hacking so far, and I think we should dig into it more.
Okay, thanks.
Cool, I think it's done. Thank you.